Welcome back to the Demystify Sci podcast. I'm Michael Shilo.
I'm Anastasia.
Today we have Glenn Borchardt on the show, and this is the first time that we've brought somebody on to the cosmological discussion who is championing an idea which is an alternative to the Big Bang, and that idea is essentially eternity. And Glenn has extended his ideas about eternity to the infinite at all levels, right? So infinite complexity of the organization of matter, infinite complexity in the organization of the cosmos. And it's really made for an interesting platform to interrogate some of the basic principles within Big Bang cosmology from a skeptical standpoint. And we're not usually able to do that. When I think about the people we've had on the show, Brian Keating or Ethan Siegel, these people who are deeply entrenched in the standard academic narrative, which is, one perspective and it's worth looking at. But there's people like Eric Lerner who for a long time have been really beating a different drum. And so today we're going to sit down and talk about some of those different ideas.
If you like what we do, leave comments, tell a friend. We grow through word of mouth, and that is absolutely the best thing that you can do for us, is tell somebody that you found this awesome new podcast. If you've done all of those things and you're still looking for some way to support us, consider joining our Patreon at patreon.com/demystifysci. For just a couple dollars a month, you can help us grow the project. You can help us make it so that the project is the only thing we focus on. We want to have in-person interviews. We want to be able to have live events. We want to be able to give grants to people. And this is a new... there's no other way to put it except for a new institution. We're trying to build a parallel institution to the academic world of science, where we have the standards and the care that is expected of academic work, but is funded beyond the scope of the NIH or the NSF or whatever other funding agencies that people are using. Obviously, this is a very, very, very ambitious goal, but if you believe in it and you want to help us keep working on the project, consider joining up at the Patreon. And in the meantime, enjoy the conversation with Glenn Borchardt, and we'll see you next week.
The scientific revolution starts now.
The Demystify Sci podcast.
Let us see in the dark.
Everybody who comes on the show is a Big Bang proponent, basically.
That's because you're getting theoretical physicists and cosmologists. If anybody has a degree in that, they have to swear a couple things. One, allegiance to Einstein, belief in the photon, the particle that's totally empty, travels at perpetually through perfectly empty space. That's what Einstein's all about. And so that's how you get the Big Bang. That's one of the ingredients that you need. Remember, four-dimensional space-time, you got to have that too, because there's no central point where the Big Bang can be said that's where it happened and so on. So
it's almost like if you were able to rationalize these basic ideas like light and really the material mediation of light. I mean, I think it could almost all come down to that. If there was actually any concern for a material understanding of light, a lot of this Big Bang stuff, like the main two, can we just lay it out that the main two pillars are the CMB and this interpretation of redshift at a distance being expansion of something, some idea called space-time, which obviously isn't a material, but when it's convenient, it's treated like a material. It's crazy that it comes down to just that simple thing, that we haven't really got a material understanding of light.
Well, there's also the religious aspect of it.
Oh, well, of course, like culture plays into why people love it so much. But
have you read my latest book? This is what I did during, can you see that without glare on it?
The religious roots of relativity.
Yeah, and I did that during COVID. So, just wrapped it up, and it's kind of explains really that Einstein's assumptions were essentially religious. And that's why it got to be so popular. 80% of people are religious, and most everything he's talking about there is imaginary, like the imaginary photon and so on. And of course, he eliminates ether. The only problem with that was it had been proven to exist by Sagnac he had a really good experiment that showed.
Oh, can you tell us about that?
Sagnac is 1913. He essentially showed that light was not a particle. So then Einstein invented these 8 ad hocs in order to make light still be a particle.
Wait, can you explain the Sagnac experiment, though? Because I always was under the impression that the Michelson-Morley really killed off interest in the ether, but you're saying that there was contrary evidence.
Sagnac,
can you explain the experiment?
Sagnac actually had done that with his little apparatus, and I explained that in my books and so on. And it's kind of well known, but it's ignored by people who like Michelson-Morley. And Michelson-Morley assumed that ether was independent of the Earth.
Right.
And it isn't. It's what you hear about, a lot of dark matter and so on. That's essentially decelerated ether, because gravitation involves ether particles colliding with things. What happens when a particle collides with something?
Well, can you back it up for me and explain the Sagnac experiment? I really wanted to understand that.
Yeah, okay. The way you get entrainment is like you do with the atmosphere, right? So you've got the atmosphere is entrained around the Earth. Ether is the same way. Part of it is. And the reason it's entrained is that I have this paper on the physical cause of gravitation. And it started out very simply saying that gravitation is an acceleration, right? It's an acceleration.
That's generally how like the equivalence principle is interpreted. But I want to hear about the Sagnac experiment. Are you gonna explain that to me? Can you explain that Sagnac experiment to me?
Oh, he's got a wheel going around, and he's talking about light being emitted, and it's essentially traveling through the ether, and it's not being emitted as a particle. And so that's why he gets a fringe in the experiment that he does. It's complicated. It's a little hard to explain.
Can you tell me how to spell that? I'm trying to look it up, and I'm not.
Oh, Sagnac. Sagnac. It's Sagnac.
Okay.
Yeah, Sagnac. If you look that up on, there'll be one thing you have to realize is ever since Einstein, physics has become very regressive. And I call these fellows that still do theoretical physics essentially regressive physicists. And I consider the people who are in favor of the Big Bang to be cosmogonists. Have you ever heard of that?
Yeah, it's like religious creation stories.
Yeah, that was actually in the very first paper that was written on it, remember, by Lemaitre, the priest who invented the Big Bang. His title has cosmogony in it. Cosmogony is the study of the beginning of the universe.
Yeah, it's funny. It's funny. The Pope was such a huge fan of Lemaitre's work that Lemaitre actually had to write him a letter and tell him to stop promoting it because it made him look bad.
Is that right?
Yeah.
So anyway, that was dropped, and I use it all the time because cosmogonists are people who have assumed the universe is finite, and the big challenge right now for people is to convert from the idea of finity to the assumption of infinity. So in my first book that I came out with, I don't know if you're ever teaching a scientific philosophy course, this is what you would want, 10 assumptions of science. Now, the reason there are no 10 assumptions of science at the moment, or even in this, before I wrote all this stuff in 1980, by the way, is that they're contradictory. So they don't, and mostly they're religious, so that it's a real bag of. So one of the problems, I think, what I would like to say this is that, and I think you were hitting on it too, Sean, that what you have is matter as one phenomenon and the motion of matter as another. And one of the things that a lot of the physicists do is they they have what I call motionless matter.
Hmm.
Matterless motion, excuse me. It's there's that too, but matterless motion.
Yeah.
Yeah, and that's what energy has typically been thought of as. In other words, Einstein said, well, E equals mc squared, and what happens is that matter is converted into energy.
Mm-hmm.
And energy is thought of as this matterless motion floating up into
it's
space.
like some sort of magic ball of stuff,
Yeah.
but not stuff. Yeah.
But yeah, in order for you then to be in theoretical physics, you got to believe this stuff. They tried to teach me this when I went when I was was a freshman? Yeah, right. I think it was physics 1A, okay? And they tried to teach me stuff about four-dimensional space-time and all this other stuff of Einstein. And I got a C. That's the only C I got in college. So I buckled down and I said, all right, I've got to learn this physics. So I got to do this by listening to this professor during summer school. And an 83-year-old guy taught me physics. You know, it was this huge book, Sears and Szymanski. I don't know if you know much about physics, but that's a big textbook. And the last half of it is what he taught us. And it was mostly classical mechanics. That I could understand. We had problems, you could work them out, and end up getting A+ in that one. So that's where I'm at. It's matter in motion. That's it. And like you were alluding to, and right now that's not the case. Definitely not. And if you try to get a degree from any school, especially like Berkeley, where I taught for one term, there's this guy Joseph Silk was there, and he wrote the Big Bang book, about 3 versions of it, 3 editions. And so, and like all the big schools, they're all pushing the Big Bang really hard.
I came upon the Sagnac Experiment, and so what it is that it's basically a self-contained interferometer where you have a light source and a rotating ring and a detector that's looking at the phase shift of the light, and you send light going in 2 directions around the ring, and if the ring is stationary, there's no interference pattern. But if the ring is moving, there's a phase shift in the light as it comes to the detector, and that phase shift is related to the angular momentum of the ring, so it increases as you spin it faster.
Okay. And how does that disprove? How does that prove the ether, though? Just because there's a drag of some sort?
If light was a particle, you wouldn't get a fringe. That wouldn't happen.
Well, the fringe is the
interference, I guess, the phase delay.
But there's something to do with the rotation that matters here, right? Because, I mean, they'd known already by the time that he was doing this experiment the fringe pattern of light's interference, and so there was the oddity of the wave particle duality of light. So the curiosity here is why, when you move the rings
are reflecting, by the way?
You can do it on a fiber optic cable. Anything that contains it's a ring made of mirrors in the original experiment, but you can do it with a fiber optic spiral that contains the light within it. But there's something about moving it relative to the source that causes interference, and that's, I think, the idea that it's a self-contained system that can interfere with itself, which suggests some kind of material drag on the light that's propagating through it, because if it's a material thing and the speed of the ring is moving the light that's traveling in the direction of the ring's speed will move along the path faster than the light that's moving against the direction of the ring's speed. And so that gives you a material sense that there's something that's actually happening inside of the ring where the light is interacting with the ring itself in order to be disturbed in a phasic way.
That I understand, but I'm not sure how it proves. Just that there is a mediator and some material interaction going on here.
Yes.
I guess. I got you. That's cool. I want to read more about that for sure.
Yeah, it's a cool experiment.
Yeah, you'll have to look at my little analysis. I think an infinite universe theory, that's this other book. This one. I've got it in there. So it talks about, does Sagnac prove light is a wave and not a particle? And it does. And he was very direct. He put that in his title. He had 2 papers on it, and he said, this proves that there's an ether. So there has to be, in other words, it's like in order to transfer motion from one place to the other, you got to have some kind of medium like you do for air, right? That's how you can hear people and so on. And light has to be the same way.
It always perplexed me that people, even when I first learned about the wave-particle duality experiment with the double split, it always perplexed me that people didn't interpret the dots as some sort of threshold of detection, essentially.
Yeah.
I always thought that was very strange. And then we had a gentleman on the show, Eric Ryder. I'm not sure if you know him or not, but he's done some cool garage work, essentially demonstrating that it is indeed a threshold effect for these detection events. And I always thought that was very strange. It doesn't seem like a huge leap of intuition to, especially when you start doing other biological or other experiments in a lab, you realize that all of your detectors have thresholds. You have to dial that in, and whether it's chemoluminescence or a voltage on some engineering project like voltage gated switching, there's always some threshold situation, and I just always thought that was very strange.
Definitely is.
But that's kind of what I really want to try to understand, and maybe you can help me, is why people are so married to these ideas that seem so counter-rational to me, right? This idea of something coming from nothing, whether it's, even if it's just a disturbance of some vacuum field of energy and material or whatever, it still doesn't have something to start it up, in terms of the Big Bang. Or why do people love that so much? I mean, most of the country, well, not most, but certainly religion is less popular today than it ever was. And still, this is just really gotten under the skin of, it's really, really grabbed their hearts for some reason.
Oh yeah, right. Well, if you can believe in walking on water and virgin birth, you can believe this stuff too. So.
But people don't anymore, is what I'm saying. Like, I don't.
But remember now. Did you never have a background in religion?
I grew up religious, yeah, for sure.
Yeah, I was religious for 20 years, and it was second nature to us, right? That's how it was, and. So now you can't say that you've eliminated all those assumptions automatically. They go away slowly, and that's the situation. And this is why I did the 10 assumptions, because it outlines, 10 different points that really are going to be able to use. You can use in order to distinguish between imaginary stuff and real stuff. And what we're dealing with here is a lot of imagination. Remember, Einstein said imagination was more important than reality. For him, that's where he got off the boat right there. And that's what he was doing. And it got very popular, that's for sure. And
I think that I actually just saw the Einstein quote this morning on a separate page. And I think that the quote is, imagination is more important than knowledge, not reality.
Yeah, same thing. But knowledge is reality. That's what you have to realize.
Interesting, because I read that to be more like you have to think beyond what you can necessarily see. Like you can imagine things to be real that you haven't seen yet. That's
true. And so I do the same thing with ether. See, I have an idea of what ether particles are like. I use Planck's constant in order to calculate the mass of an ether particle. It's 10 to the minus 47 grams. That's the size. It's like 10 to the 20 ether particles in an electron. See, we know the mass of electron, so you can calculate then if you consider that in Planck's constant, essentially talks about the smallest amount of motion possible. And so from that, if you assume that an ether particle hitting a baryonic particle is the smallest motion, then my assumptions are, I do this speculative. I'm not saying this is exactly what ether is, but I also think that ether happens to be a vortex. And the reason I say that is that light is a T wave, transverse,
Hmm.
and it's not an L wave. And so to be transverse, it would be quite unlike, for example, nitrogen, which is what is in the atmosphere, where we know it's a P wave. It's I would say, an L wave. I'm trying to keep these straight. T and L is better
Well,
than all these.
there's only one real transverse material motion in the universe that I'm aware of, and that's twisting on something. Like that's the only way that you can generate a transverse wave in nature from that I'm aware of. Yeah. I mean,
Yeah.
you can simulate 1 and 2 dimensions at the surface of a pond, but if you just want to affect a transverse wave right now, you just have to twist on you can twist on your finger and apply a sheer transverse force to it, essentially.
Or
That's
like a
it.
fixed string that you're like going.
Yeah,
like,
anything really, yeah, that you want to twist on. That's the
well,
only way.
steel has T waves, so
They're twisting
anyway,
though.
yeah, as a solid. So I then figure, well, the only way you can get a T wave would be for it to be a vortex and not round like a nitrogen molecule might be. So I think that's probably why you get T waves.
So you are, I guess that it sounds to me like you are a proponent of some sort of Lesage-like push explanation for gravitation and things like that.
Right.
I see.
Yeah.
I see.
Well, remember, gravity is a push. It has to be, because otherwise, how can you get acceleration? If you look at Newton's law.
Yeah, I'm not convinced it's an acceleration. I'm aware that that's the popular interpretation of it, but I'm not sure that
if you fall far enough, you will realize acceleration.
Well, you obviously get acceleration when you are moving through a gravitational field, but gravity itself seems to me to be more of a pull force, a tension. And then, of course, if you move through a tension gradient, you're going to accelerate.
There are no pulls in nature.
There are, actually. If you just lock two of anything together, you can pull on them.
Oh, let's try this again. You take your finger and lock on the other one. You're pulling it.
That's right.
You're not. Excuse me. You're pushing it. In other words, if you open a door knob, right, and what you have to do is put your finger around it, and then you have to do a push. This is not a pull.
Well, hold on, but there is a push, but there is also a pull. Like you are pushing.
No.
Well, it's a definitional thing. Like obviously, a pull is just a push applied from the reverse side of it.
Yeah, exactly.
But definitionally, it's still a useful concept, right? Because you attach cables to things and you lift things, and you can put that negative sign on, and it's still understood that you're really. I mean, if you want to just generalize it all, it's really just pressure. It's just like, how is the pressure being applied?
Yeah, and that's essentially what gravitation is. So what we found out, I don't know if you heard of the Rebka experiment in 1960. They called the result a result from time dilation.
Yeah, can you explain the experiment for people?
Yeah, I can explain a little bit. What they did is have this 23-meter tall, I don't know, chimney or whatever, where they shot essentially electromagnetic waves as moss water. And they were able to find that you got a blue shift when the light was going towards the Earth, and a red shift when it went away. And the big thing is, well, how do you explain this? And the way we've done it in our work is that essentially there is a difference in the pressure going away. Its pressure actually is greater than near the Earth. And because it's greater, it's more active particles and so on. When light travels away from the Earth, its velocity actually increases because it's going through a medium that is different from when it goes towards the Earth. Then it would be having shorter wavelengths. That's why you get the blue shift.
So you imagine the ether is more dense near material bodies.
And its activity is greater further away. So
and this is, by the way, this is generally interpreted as gravitational redshift. Is that correct?
Yeah, exactly right.
I see.
Doesn't really have anything to do with gravitation, but it's one step removed, but still it's what they call it. I don't particularly like. It's a misnomer, but
Well, yeah, it's one of the many. It's one of the many cosmological sort of redshifts that are interesting because on one hand they're treated like Doppler shifts, but on the other hand they're not, right. They're the expansion of some concept called space, which is very perplexing.
Yeah, and see the Doppler shift, of course, occurs in cosmology, but at great distances, it's got to be essentially a distance effect. So it's a loss of energy over distance. See, that's why Einstein, in order to interpret that stuff, he has to have perpetual motion of a particle. And no particle has perpetual motion. If that was the case, every pitcher in the world would be throwing bullets at to hit her.
You mean like why light doesn't lose energy over distance?
Yeah, well, it doesn't lose velocity. Remember, velocity in media is determined by the media, not by the source. Remember, Einstein has to go through all these conniption fits about the source, and all the observers are supposed to get the same result and all that kind of stuff. Well, that's because it's a medium, and the medium, it's like same thing as air. It's your source doesn't change what happens. Like the velocity is determined by the air. That's it. And so now, how can you lose energy over distance? Well,
Friction.
only other way, longer wavelengths. That's what.
Well, yeah. Ultimately, it's friction, like Anastasia said. It's the energy is being dissipated into the structures that are relaying the information.
Yeah.
Well, I guess something that I'm thinking of as I'm listening here is that I'm surprised that you would have a particle nature of the universe. Like, why? Because if I'm thinking about classical mechanics, I feel, and this is going to sound really woo, so forgive me, but I feel like the demarcations that we give to objects and substances are arbitrary and a product of the way that we interact with the world, right? So because we are beings that are in a specific time frame, I look at the guitar that's across the room and I see the wood that it's made of, but I don't see the tree that it came from and the, worm food that it will one day become. But nature seems to me to be a true continuum. And so I'm surprised that when modeling the ether, you model it as particles rather than something continuous.
Yeah, that's contained in the scientific worldview. And I should point out this. This is my magnum opus, and
the scientific worldview.
Scientific worldview, and one of the hubs is that understanding the universal mechanism of evolution, and you probably know about systems philosophy. What I did, as I said, I don't agree with systems philosophy because what it generally does is it tends to overemphasize the insides of things and sort of neglects the outsides of things. Not entirely so, but what I finally decided, and I had to come up with a word for this, in order to study a thing, like you're saying, a tree or a piece of wood or something, I call it a microcosm. And then what is outside of it is the macrocosm. And what happens, you have this interaction between the two. Everything is interacting with its environment. And so we had to come up with a name. And this, my friend Elizabeth Metelke helped me one time. We were at a kitchen table and we said, what is a good word to understand this? And remember, there was environmental determinism at one time. And
what is that? Tell us.
Environmental determinism was sort of like an overemphasis of the environment. So it would be when you talk about behavior and stuff, I suppose Skinner would be involved in some of that stuff. You talk about the environment being really powerful. And I was saying, no, it's both the thing and the environment are equally interacting. So we invented this word univironment,
Hmm.
and that combines the two of the microcosm and the macrocosm. And so
like
by
that.
using those definitions, so when you look at any part of the universe, it's infinite, not only macrocosmically, but microcosmically too. So you'll have ether particles. In one of our books we wrote, Universal Cycle Theory, we talked about a hierarchy in which you have sort of like Aristotle said, infinite divisibility of matter. And so you just have things, because everything has to have something inside of it to have matter.
Well, in order to move, it has to have subunits, essentially.
Change shape.
In order to change shape, sorry.
Because
To move, it would require that too, assuming
Wouldn't
they're connected.
Well, because you could have something that didn't have any subunits that was hit by another object that didn't have
If they're little
subunits.
bouncy balls, you're right. Yeah. But even then, to have elasticity, like to collide and bounce, I don't
As
know.
opposed to just...
Breaking, or I don't know. It's hard to imagine. I guess it boggles the mind to imagine something that doesn't have divisions below it. It all of our material science understanding falls apart. So I can kind of see what you're saying. I guess, like for us, I think this is like along these lines for us, we're very allergic to the word particle because it's one of the most abused words in all of fundamental physics. Because when
Did you see that hilarious Quanta article, which was "What is a particle?" and it was basically just
whatever you want.
It wasn't like that, but it was basically I think there was Natalie Wolchover. She'd gone to 6 different top tier physics laboratories that were studying particles, and it turned out that they did not have a universally agreed upon definition for particle.
Right.
Let me see if
I mean, it really comes down to, and like in my estimation, the best I can steelman their position is that a particle is a dynamic occurrence. It's an event because it has momentum, right? It's in motion already. And so it's a measurement or a predicted measurement as the outcome of some, it can either be the solution to some dynamic set of equations, or it can be a prediction of something. But it's not a physical body like the chemists would think of a particle, right? Or a biologist would think of a particle of dirt. It's not a physical body. It's a measurement, right? And that's what makes me nervous about that.
Just a second.
That word.
All right. What I have finally there's a difference between mass and matter.
Oh yeah.
Matter I define as an XYZ portion of the universe. Now that's what your particle would be. XYZ. It can be any size down to infinity and up to macro. So that's really important. Now mass is, do you know what mass is? Mass is the resistance to acceleration. Think about that a little bit. In other words, F equals ma, mass. All right,
I mean, the problem is most people, when they say particle, they actually imply that it's got a dynamic component to it, right?
I can read you these definitions.
It has momentum.
A deformation of the qubit ocean, vibrating strings, a many-layered phenomenon, and an irreproducible representation of a group, a quantum excitation of a field, a collapsed wave function. They all do seem to have motion inherent in them, right? Because if you come down to the bottom of quantum field theory, you get the definition that a particle is a measurement of the changing vectors of the quantum field. They're measuring some kind of change and calling that change the particle.
And I feel like it's unintelligible to start with motion and try to build something out of motion. Like motion requires 2 locations of some body, essentially.
That's exactly right. And that's why the fourth assumption of science is what I call inseparability. You cannot have matter without motion and motion without matter. Now that's lost on physics today. We have all these complications like you're pointing out. It's an equation, it's a measurement, it's like time. The physicists do not know what time is. If they did, they'd have to drop the Big Bang entirely. Time is motion. That's all it is.
Motion.
Yeah, it's like some measurement. Yeah. Measurement of change.
It's not a measurement because look at dinosaurs had time.
Well, did
not
they?
bad.
I don't know
Well,
if they-
hold on. Dinosaurs had time only by measurement of the biological processes that happened inside of them, gradually broke down, stopped
they-
being functional,
but they
and
didn't
then led to
remember
their
what
deaths.
you got to remember.
Like, they didn't
what
have wristwatches. I'll agree with
Remember
you.
what measurement is. Measurement is, and I've done a lot of experiments. Measurement is a measurement. It's
Well,
a measurement.
It's
That's all it
counting.
is.
Well, it's counting, right? So you create yourself a little window, and you're like, inside of this window, I'm just going to look at what happens.
Yeah.
And then you look at what happens inside of your window, and you then make conclusions off of the things that happened in your window. And if you
But
really
that doesn't-
believe,
But that's not what time is. See, time is, we use all kinds of instruments to measure time, just a simple alarm clock or whatever. You wind it up and then it moves and so on. And the earth is rotating and revolving, and those are measurements of motion.
Yeah,
We
standard
just-
motion, right? They're
Yeah,
standardized
that's all,
against.
That's all it is.
So
And
you essentially you compare any motion you want in the world versus some standardized motion, right? That's
Exactly.
repetitive and
Right.
cyclic and dependable and reliable,
like,
as
if
much as you hope that it is.
If you just had, like, imagine a single object universe. You just had, let's say that
Single
you had,
object universe couldn't even move.
or well, that's what I'm saying. Like, you just have a single object universe. You can't possibly have time. And the only time that the only emergence of time occurs when you have two objects and you can measure how they're moving relative to one another. But honestly, ideally, you'd have a third object, which is the one that you can stand on that doesn't move while
Yeah.
you watch the other two move. Like, a 3-atom universe is your minimum for
If
really.
the atom can see.
Well, yeah, like, imagine you're an atom that can see. We're getting in the weeds here. But, like, a 3-atom universe is the minimum that you would need in order to be able to tell time.
to measure it.
Yeah.
Yeah, the time would still occur anyway. So it would, that's the point that I always make. That time is motion, and there are all kinds of motions, an infinite number of motions, right? So that's why you can measure it however you want. But you always have, I agree with one thing about Einstein. Everything in the universe is in motion with respect to other things, okay? So, hey, that's where I'm with Einstein. Pretty much not anything else, though.
Okay, so while I was looking up the pound Rebka experiment, there's this little thing at the bottom of the article which talks about local position invariance and suggests that clocks are unaffected by gravitational potential. Where do you stand on that? Do you have an opinion about the effect of gravity on clocks?
That's not true.
Yeah, obvious. I mean, all the GPS stuff kind of proves
Again,
it.
it's because, see, when you do the GPS, you have to do a calculation related to the altitude that you're at.
Okay, so the clock rates are independent of space-time positions. The measurements will differ in the elapsed time displayed by two clocks, but that's because of their difference in position in the gravitational fields, not because they're actually running different.
But see, they don't.
But how could you separate those? I'm sorry.
That's what you call time dilation.
Yeah.
And it's all this twin paradox stuff, and it's all really silly. And so,
but people love it. They
I
love
know.
it.
Yeah, why?
so
Okay,
great.
well, so let's. I really
We're
always
gonna get
like
so
to.
much hate in the
I
comments
know,
on
but I
this.
really always love to unpack why people love these things
Yeah.
and where they come from. And so basically, the way that I'm reading this is that what it's saying is that the difference in the clock of a Earth clock versus satellite clock isn't actually that the clocks are running on different rates because they're not affected by gravity. It's the fact that you're in a different area of a gravitational field, and so you're in two different frames of references, and the comparison between them gives you this apparent shift. But Einstein's twin paradox then goes forward to suggest that that's a real shift.
I mean, I just don't see how you can possibly separate out what your measurement device is doing from, like Einstein blaming it on a gravitational field. Like a field is a set of measurements or predicted measurements. So I don't see how there's any explanatory power in saying a field did something, right?
No, I agree.
I mean, it's just it's very descriptive. Einstein's equations are very accurate, but it's they're just telling you what the predicted outcome is. They're not explaining anything whatsoever.
Yeah, it has to be in physical terms of matter and motion. Otherwise, we don't even bother.
100%.
A lot of the stuff people like doesn't involve matter and motion. Remember, you are looking at these days it seems like every other movie is a sci-fi thing about time travel or this other god-awful thing. And people really love that stuff,
God, they
you know,
love it
because
so
it's
much.
imaginary, it's magic. It's sort of like the fairy tales that were told to you and so on. And we, as a species, we're really juvenile. And
Well,
it takes a while
we,
for us to come around, you know?
well, you can't take. I don't know if you can take that out of people. It's like, especially
No,
with
no,
the sort of, I don't want to say death of religion, but the unpopularity of religion
no.
in the
Well,
West. It's like people need something. They need some magic in their lives. They need something to believe in that's bigger than themselves. And I think that the physicists are willing to give it to them.
yeah.
And so people are like, well, if I can't have religion, at least I have quantum physics or something. Which is like, I agree.
Yeah,
It's kind of it. I think that it's tragic because I think that ultimately it's probably holding us back from
it
harnessing the
is.
true powers
Yeah.
of nature. And also just from a pedagogical standpoint, it's really sad when you're a kid and you try to understand how light works or something, and you end up with all this magic show stuff. It's just,
Exactly
it
right.
really was heartbreaking to me when I was little.
Yeah.
It still kind of is, but
It's sort of like, but remember, a reason it'll be with us forever is
no, no.
that, well, as a baby, you have this blanket over your head at some point, right? And you can make the world go away.
Mm,
But you're trying to figure out, well, you know, about material permanence, matter permanence, and so on. You have to learn that.
mm-hmm.
We learn cause and effect. And that's what we learn. You know, if you do this, then that happens, and so on. And as a little baby, you are, how would you possibly know what's real and what isn't real? And eventually you can grab stuff in your hands and the little kids play with it and they're enthralled with it, just like the juveniles are in our society. They're enthralled with this learning of is reality and what isn't. And the imagination is important because, like you were saying, Anastasia, you were saying, look at you have to use your imagination, and I agree somewhat with Einstein. It's not more important than knowledge, but it is very important because in science we always have to imagine stuff before we ever. You got to have a theory to look for something. You don't. I've never done any scientific work that I've done without having a theory first, an idea. Well, I'm going to walk on the soil here or do whatever I'm going to do. That's what I'm going to have to know about. I had to have this theory. And basically, before I started all my work in 78, I was still a big banger in 1978, early on. But by the end of 78, I had finally given up on it. I just
What
couldn't.
happened?
I was reading a lot. I read a lot. You heard of New Scientist, the journal, and they would have a lot of Big Bang stuff and so on. And I would read that stuff and say, you know, like you are, and that's great that you guys are a little skeptical about this stuff. But I would look at that and say, that's really crazy. And so finally it just got to be too much. And I actually, on my job, I ended up asking for part-time so I could write the scientific worldview, because that was really what I was, you know, puzzled over, concerned with. And I had some ideas that I think I read like 495 references or something for that book. And so that, and I was always had a problem just concentrating on one little specialty. You know, I've been in a dozen of those, and you know, after I learned them, then I went on to the next one, and so I just really was interested in the universe. Now, a lot of times when I talk to people, they could care less about the universe, whether it's infinite or not. You know, I'll get on the ski lift and somebody will say, you know, what do you do? And so I'll tell them, you know, theoretical stuff. And they would say, oh, yeah.
Yeah, they probably say, well, can you tell us about the Big Bang?
Yeah. So about that, a lot of people don't even know about the Big Bang. It's amazing. because it's all over the news all the time, as far as but see, I'm biased because I only look at certain things like most people, you see what you want to see.
Well, people want to have interests that relate to them personally. And I think that it is an interesting psychological phenomenon that there is a crew of people that appears to be really interested in things like the shape, size, scale, beginning, and an eternity of the universe. It's a pretty weird... sometimes I kind of snap out of it and I look around and I'm like, how is this possible? You think about the all of the farmers, all of the day laborers, all of the truck drivers across all the whatever it is that you're doing. Everywhere that you look, there's going to be somebody who is interested in these cosmic questions.
Sure.
And that's so strange because it literally seems to me like a personality trait. Because most people are so focused on the day-to-day and the immediate questions of survival and entertainment and satisfaction that they never, shake their head and ask the questions of the universe that they could ask just literally by standing there and looking up or looking around or doing whatever.
But don't you think people have to wonder, how is it that we're here? What is all this stuff around us? Why is everything so infinitely different? Why are no two snowflakes alike? All that's telling you stuff about infinite universe. That's for sure.
I think that it has at least something to do with Protestantism. Because if you come from a religious tradition that tells you that there is no mediator between you and the universe, and I place the universe in the position of God because I kind of look at it where I can easily translate God to consequence. And I'm like, there are consequences for actions, and that is God, and that happens to be the universe. So I'm like, if you come from a tradition that tells you that there is no mediator between you and the consequences of the universe, then you're going to be standing around and you're going to be like, oh, that's crazy. That's on me. But if you come from a tradition where there's priests, which, whatever hierarchic system you emerge from, you're going to be in a position where you're like, oh, well, people give me the information and that's just how it is.
Yeah. And so you heard about the question authority. And remember, that came about when? During the 60s. That's when we were active in questioning authority. What does that mean? And that's why I see the Big Bang hanging in there another 30 years, but I don't see it going longer than that. And if you look at books, I show the reason for that. Yes, developing more international fascism before we develop international socialism. That's how it works, because people try the old thing first, and then before you're going to try the new thing, that's a lot of work, right? And so anyway, that I think is all interconnected. And so, like during the 60s, that was quite an awakening. People started to question things and so on, and even there were some Death of God books and things. You might have heard about those from those days. And then now there's the God Delusion, Dawkins' book, and so on. So you can see there's a beginning of questioning about this stuff. But normally people just take orders and that's it. So.
Yeah, I think we were talking about our religious upbringing earlier, and it just occurred to me that the religious tradition I came from didn't embrace any of the supernatural stuff. Maybe that's why I was more open to, or really? Maybe why I was so...
What was that, Unitarian?
It was just like a really diet Lutheran church. Everything was very down to earth. Like all of the lessons were about how to live your life. Like really? The deities were seen as metaphorical more. That was really? That's how my family saw it. And that's how I was always taught.
I remember I was in Synod, Missouri Synod. That's the most conservative of all after the Reformation. I think that Luther would be a member of the Missouri Synod.
Wait, you were in the Missouri Senate?
Synod, Lutheran
Synod.
Church.
It's called
Yeah.
the Lutheran church gatherings. Are,
Sorry,
You have
Jewish.
like-
Yeah, right. Anyway, so that was definitely all Bible stuff, and a literal truth of the Bible and so on. And probably that's one reason I could jump away from it, because I started doing some carbon dating, and dates were greater than 6,000 years. So
yeah.
there was a contradiction there that we had to handle, and I eventually did. So, but anyway, that's when things are really stark, like the fascists, for example, during this time, they're showing how absurd the ideas behind fascism are, so that you have to be pretty much asleep not to get the idea of what this is not good. This hate stuff is evil, or whatever you want to call it. So I think that's true. And so when you see the Big Bang falling apart in view of the web photos and so on, it's really it's very exciting for the 10,000 of us who are opposed to the Big Bang and relativity. So
Yeah, I got an email this morning from one of my former students, and he was like, Dr. DeLay, I just read that the distant galaxies are moving away from us faster than the speed of light. How is that possible? And I was just like, yeah.
no, and that's at a Z of 1.5. You know what the Z's are now? I think it's 11, pushing 13. So the Doppler effect had to be discarded. And
well, now, of course, they just say the space is expanding.
Yeah, and
which
space
is like
and another magical thing.
Well, it's weird because you push on the concept of space, and it just really means the distance between things. And it's like, well, I knew the distance was increasing. Like, that's why you said that there, but that doesn't explain anything for me. Like, there's
no cause.
You just sort of like slipped out of the handcuffs. It's not really.
Go back to a cause. The cause is object A hitting object B. That's a cause.
Mm-hmm.
Or
pulling on.
That's Newton's second law, right? And so that's so important. And that's what's been discarded by Einstein and his followers. And we're, like you said, we're behind the times because of that. A lot of it's theoretical. I think physicists in general, the experimental physicists, they ignore all this theoretical stuff.
I think it's really important. You said something about people discarding. Oh, sorry, it'll come back to me in a second. Yeah, I'm sorry. You said something really interesting though.
Discarding something.
We were talking about redshifts.
Matter in motion, right? Maybe you're talking about that.
It'll come to me.
I mean, I feel like the ability to retcon the data into the story that people want to tell is almost infinite in capability. We know that you can have a geocentric universe for hundreds of years, even when there's people that are like, hey, I don't know about that. And I feel like we live in a time where we maybe falsely believe that there's a difference between us now and us 500 years ago, where those people were superstitious, those people were easily swayed by what was written in the big important books, and we are different, we are unique, we are clear thinkers now that will be able to crest the hill of darkness and see what lies beyond. And I just kind of have this feeling where I'm like, look, this is going to be an eternal state of thought. There are always going to be people that have a vested interest in supporting institutional thought, because institutional thought takes a specific form. There are things that belong to the institution, and when somebody says, I believe in the Big Bang, they're not saying, I believe in the Big Bang. They're saying, I believe in the institution.
I remember what I was going to say too. It ties into this, which is you were saying that what has to happen is that the institution has to like blow apart. Like it has to completely fail miserably in public and have this like horrible death before people can move on. And I think that's really smart. That's a really smart recognition right
But
there.
there's also the fable of the emperor has no clothes, right?
For a while, right? But I mean, how long does that hold out even in the story, right? At some point,
I don't actually remember how the story
some
ends. Does
point,
everybody agree that he doesn't wear clothes?
well, I
or
think
do they
some
shush
smart
the
kid in the
child?
story is just like, hey, Emperor's not wearing clothes, and people are like, what? And then like eventually people kind of come out of the woodwork and are like, yeah, he isn't.
There's also all that like the ash experimentation from the 70s. Do you know this stuff?
Once,
So he did these crazy studies where he would bring people into a room and he would force them into agreeing with patently untrue statements. Like there would be a board in front of, there'd be 5 or 6 people
sure.
sitting at a table. There's a board with 2 lines on it. One is clearly longer than the other. And they go down the line answering the question of which line is longer. And everyone says the shorter line.
Well, they're all plants.
They're all plants except for one experimental subject. And then the experimental subject looks around and is like, I guess the shorter one. And it only takes one dissenting voice in that row of plants
True.
for the person at the end of the table to be like, no, it's definitely the longer one.
Yeah.
And so you have multiple things playing together, but like, I think that we cannot underestimate the love that people have for institutions and the love that they have for for figureheads and for mascots and for tokens of meaning. And as you start to the reputational wisdom of the church has been deeply undermined by the actions of the church. And so people are kind of adrift and they're latching onto scientific institutions. And I feel like if you pry their, white-knuckled hands off of that, you're going to unleash utter chaos. And so like you have to peel their fingers back from that really, really slowly because there's like a yawning pit of eels that they're about to fall into.
Well, they need another rope to cling to.
They do. And it has to be something that is
We all do.
reputable and upstanding and cool, right? Like that has a huge part of it.
That's what science does for us, and theoretical physics is supposed to do, but that's failed us too. So that's for why. Look at I hate any kind of lies, any kind of falsity. My whole life has been spent trying to discover the truth, and eyes flash when you hear the lies, and so that's the really thing. What you were pointing out was essentially a paradigm shift in how that can be quite calamitous and so on. And I remember plate tectonics. I was there when it just developed in '66. That's when I was in school still, and that was kind of interesting, because it really threw out all kinds of stuff, but I don't remember people screaming in the streets or anything like that. And it gradually happens. You convert, and I know as recently as 20 years ago, there were some geologists still anti-plate tectonics in our organization. So it was kind of crazy. And but a paradigm, I think what happens is that Einstein and the Big Bang will all just be forgotten. And then the infinite universe theory will take over. Gradually, we'll develop that. There's so much we can do with that. And it solves so many problems already that why wouldn't it do even more? And so that's why I'm looking forward to that. And I wish I could be there. You guys will be there maybe.
I mean, I think we see a similar thing playing out right now in planetary science, actually, which has really been fascinating to watch because, I've been last semester I taught like a intro planetary science course, and I had a chance to really dig into the literature, spend some time seeing what's happening. And it's wild how much our understanding of our solar system has just quietly been rewritten in the last 5-10 years, especially as we've started to see other solar systems developing.
But didn't you have like a rewrite of the textbook as you were teaching?
Oh, all the time, yeah. So I use this online textbook that updates. It's got like 100 of the, top lectures from universities all around the world that are contributing to this textbook. It's kind of cool, actually. But yeah, it'll literally update. Like there will be new sections put in like while I'm reading it sometimes, and it's kind of incredible because it's one of those things that most people don't really care about. Like they don't really care about the formation of the solar system or something. I think very few people care about that for some reason. I love it.
They must care somewhat. Look at the billions that are being spent in studying it.
But it's changed so much in the last, like the fundamental premise is maybe the big paradigm, the big picture hasn't really shifted, but we're seeing planets evolve, right? That's something that was never really considered, is like we're seeing these big gassy planets getting their atmospheres blown away. We're seeing that there's a continuum, right? These super Earths are very similar to these Neptune-like planets, and there's like metamorphosis on the table that's never been there before. And it's one of those things that I think people are just not really going to talk about. It's just going to slowly turn into a new story. And like you said, it'll just be this very long, protracted, quiet revision.
And so, but again, we're getting the blanket taken off of our head. And so we're seeing more and more stuff. Every time you send a rocket up, you find out something, and every time you look on the internet, you got infinite number of stuff. You could be reading on the internet everything else. And some of us are doing a little bit too much. And so that's essentially what's happening. We are just inundated with infinite this and that, and so on, just goes on and on. And you take a look at a tree once, you won't find two leaves on a tree that are identical. They're similar. Remember, the ninth assumption of science is that any two things have similar characteristics and dissimilar characteristics. They're not identical. It's like there's no identical twins, really, if you studied that a little bit. So that's the interesting thing. And it turns out that without the universe being infinite, we wouldn't be here. It's all these mess ups, these variations that allow us to be here. Because remember, the atomists said, oh, well, the fundamental particle is a little sphere, right? Matter, right? Well, it turns out that's not even possible. We have a continuum between perfectly empty space and perfectly solid matter. Now, there are people hypothesizing that perfectly empty space, which is imaginary, that it actually exists, and that perfectly solid matter maybe exists. But it turns out the infinite universe won't allow that to happen. And everything consists of a little what we call empty space and a little bit of solid matter. And that's just how it is. And so everything is in the range. So this is a religious assumption. So the opposite is called absolutism. So yes, somebody would say, you couldn't have solid matter, and that's a finite particle theorist, by the way. And then you can have perfectly empty space. That's Einstein, by the way. And even they've done that, by the way, too, I was going to mention. In 1920, he said, oh, there could be an ether. And nobody listened to him.
Wait, are you talking about the Leyden Address?
Yeah.
Yeah,
he said that. He said that.
Well, he said that it was a non-kinematic ether that he didn't even know how to begin to think about.
You're great. You got that down.
This is my one Einstein fact that I can pull out of the pouch.
But to be non-kinematic, see, that's the stationary ether idea. And it's, of course, if he'd listened to his own assumption that everything in the universe is moving with respect to everything else, then he would. But he was really into affinity. And so affinity would be you have a perfectly empty space and solid matter. That's the kind of the connection that you have. And it's very common that you use that. And
it's interesting because if you look at the quantum description of the electron, let's say the outer surface of the atom, if you transform it by charge density, so that you basically say where the charge is found, you get a function that goes off into infinity. And it does seem to suggest that the material that you're measuring at this electron measurement thing is rarefied at distances farther away, and that it's denser at regions closer to the atom. But it does seem to be a continuum for sure.
Yeah. And that same thing, like the deceleration theory I was telling you about in regard to gravitation, same thing. So you get, when things collide, one slows down, one speeds up. And so that's all you're talking about. And in quantum mechanics, same thing. A lot of times you think of quantum mechanics as being all that different from baryonic mechanics, but it isn't. It's matter, see, but once you get to the small particles like that and experiments and so on, you can interpret them in the way that you wish. If you want to make it religious or imaginary, go ahead. And they do that. That's like some say this particle is in two places at once. How nonsensical is that?
Oh, I was going to ask you. Oh, you live in Walnut Creek where Clauser lives. John Clauser, the guy who got the Nobel Prize just recently. You guys are neighbors.
Haven't met him.
Okay, I was wondering if you had accosted him somewhere on the street to be like, sir.
Yeah, if somebody gets a Nobel Prize, I stay away from them.
Fair enough.
Normally, although maybe I would debate Neil deGrasse Tyson or something someday. Who knows?
Well, because
it's not much of a debater. I watched him debate. Who was it? Somebody posted him debating a little kid, some quiz.
What was he? 8-year-old kid.
Yeah.
It was. I put him out on my blog. I don't know.
Okay, maybe that's where I saw it. Yeah.
Yeah. It was so cool. Where he says, "I believe in conservation of energy, which is really the conservation of matter and motion."
Yeah.
Right? So but that's my number one. I've got 20 falsifications of the Big Bang, and number one is that. And he hit it right on the head. I don't know if he read my stuff or what.
No, that's the funny thing, though. Is I'd never read your stuff either, but I very much had come down along many of the same conclusions. I think because they're probably true. And when a lot of people see something that's happening and they realize that the explanations they're given are unsatisfying, then they're driven towards other explanations, and there's not too many other ones that you can come up with when you just look at the equations of state for all of these different phenomena. You're left with that interpretive step, and that's what I think is really fascinating, because in the scientific education pipeline, very little attention is given to that interpretive step. Right? It's all we stick with the evidence, but look, if there's a trial going on, you don't just lay the evidence on the table and go have lunch, right? You prosecute your theory of what happened, right? And the reason that you even have a trial is because there's multiple interpretations of what the evidence means. And that is, people don't realize that.
You hit that right on the head. And when you have incorrect assumptions, you don't want to hear about that. And if you look, the one thing that you do when you take down a paradigm is you have to look at the fundamental assumptions. You can't just do the math and stuff like that. So that, for example, gravitation can be a push or a pull. The equation doesn't tell you which, right? So now the big question is, well, why we have this fantastically absurd Big Bang theory? And it's based on, and I learned early on, I just sat down, I said, in beginning my work in 1978, I said, what are the assumptions these guys are using? Because they're not the ones I'm using. I'm talking about cause and effect, things banging into things, and they're talking about something else. And what is it that they're doing? And that's why I did these 10 assumptions. And the interesting thing, I got to explain a little bit how I came to that. I was at the Berkeley Library about 3 times, and each time I was looking at this title, Essay on Metaphysics by Collingwood, 1940. And I passed it up each time, and I said, well, metaphysics is BS, and in science we don't use any of that. And finally, I picked it up, checked it out. Well, it's true. The book had 2 parts to it. One was BS, and the other part was solid science. Mm-hmm. And what Collingwood said, he said that in order to find out what the fundamental assumptions are, they each have an opposite, and they can't be proven. Like finity and infinity. You can't go to the end of the universe, prove finity or infinity. It's not possible. But you can assume one or the other. And also, if you have more than one, they have to be consupponable. Now, that's a word that I'm the only person that uses it.
Actually, David DeHilster brought that one up for us earlier.
I was about to say it. He dropped it as if it was a word that was just...
He kept going. We're like, hold on, you got to break that down for us.
But it makes sense. It's with supposition. So you're saying if you assume one, then you can assume the other, and so on. That's how all 10 of these are then consupponable with infinity. And the opposites are like infinity and so on. There's causality and acausality, and you can make either assumption. So now when you were talking about, well, it's interpretation, we have all this wonderful data, and how you interpret it depends on your assumptions. And if you're using the wrong assumptions, you don't admit that. That's what the problem is. Like you're saying, why don't they tell us, what are your assumptions that look at the main assumption that the universe had a beginning? That's infinity. That's cosmogony. And they don't mention, I am now going to assume the universe had a beginning and then do the Big Bang stuff. They don't say that. It's all kind of hidden, even though it's quite obvious, that's what it is. And some people have said,
so weird, like
the universe some say that the universe is not finite. And they'll say, well, there's dark energy or something, and they don't know what energy is. So that's what, there's no dark energy. Remember, there are what I call matter motion terms. So you multiply a term for matter times term for motion. So momentum is that. MV equals P. That's momentum. Okay. Is there such a thing? No.
That's an idea.
You'll recognize what the equation means when that linebacker hits you. If you're 300 pounds, you might get knocked over if the guy is moving fast enough. And that's what momentum is all about. But it's not a thing. It's a matter motion term. It's a calculation we use in physics to understand. F equals ma is the same thing. There's no such thing as a force. No matter all these regressive physicists talk about forces, the four forces and all that stuff. There's an infinite number of forces. Motion is what's going on. Is matter in motion. And that's what energy is about too. 100%. So energy is equals mc squared or 1/2 mv squared. That's what that is. It's in a calculation. And so dark energy, if you really, really believe it's dark and there's no matter connected with it, that's matterless motion. Impossible. And
well, dark energy is it comes out of the theoretical predictions necessary to try to cling to the Big Bang presupposition.
Exactly.
Yeah,
that's what they're doing.
The funny thing is, though, sometimes I'll just talk to normal people, who
sometimes.
Not scientists. Every once in a while, I'll talk to somebody who's not a scientist. But I talk to normal people, and I propose the idea of eternity to them. And, maybe we'll be like talking about the Big Bang and what's so bizarre about it. And I propose the idea of an eternity, and it's almost like people are just like, what? That can't be. Like, what? How's that? Because their own lives have a beginning and an end, right? Everything to them is a closed system, right? And so it's almost inaccessible to people. I feel like this concept of eternity. It's like, well, how long? You're like, they're like, so like a really long time. You're like, no, like an unending amount of time, actually.
Yeah, right. And I've had people that would mention that too, and then others who say, I can't believe it ever had an end to it. Would there be dragons there or something? Is it James Webb going to find out what it really is? No, that's not. So it baffles the mind to think of infinity. Now we've got a lot of data in support of infinity. You know how many galaxies there are?
A lot.
A lot. That's a good answer. Okay, you know that the Milky Way has, how many stars are in the Milky Way?
A lot.
I don't know. It wouldn't matter to me because I can't really, it's hard to really picture numbers above 100. I mean,
400 billion stars in the Milky Way.
It doesn't clarify anything for me though.
Well, hold on. Where are you going with 400 billion in the Milky Way? How many galaxies?
And how many galaxies are there? There's 20 trillion galaxies. That's pretty close to infinity in my mind. It's not infinity, but it's close.
Well, it's also
like evidence.
Are you ever going to stop? Are you ever going to stop finding them? Right? I mean, if you had looked at the James Webb and glanced at the very edge of the universe and had found this primordial soup, then I would be willing to be like, okay, there's something weird that's happening. there's a timeline for the universe. Perhaps there was an origin point, but you keep looking farther out and you keep finding fully formed
The
galaxies.
same stuff.
Yeah,
And it's the
right.
same stuff. And so I think that for me, it's not a numbers game, but it's more a terrain game. Where as your telescopes get bigger and bigger and you look farther and farther out and you just keep seeing the same stuff, your assumption has to change. However, I can also imagine on the level of a biological metaphor, if the entire contents of the universe, taken to be everything that we can see, everything that exists in our light cone, however you want to call it, is bounded by an impermeable membrane, then there is an end, but not necessarily an end to all kinds. It's just that there's another membrane on the other side that you would have to break through in order to reach whatever's there.
It's like a multiverse theory.
Or it's like a body theory. Like, I mean, this sounds so woo, but I think about it in context of, okay, there's a lot of panpsychists and people like Michael Levin that believe that consciousness and will goes all the way down to the atomic level. And I'm inclined to agree because there's not a place where you can point to it emerging wholesale to be what we embody. And if you start to discount it, you end up in a place where you're like, babies can't feel pain and you're doing surgeries on them without anesthetic like they did until the 80s. And so like there's all kinds of weird things that happen when you arbitrarily place consciousness and awareness somewhere. So like let's say it's a continuum where complex awareness, atoms is simple awareness. But if the universe is fractally organized, why could we not be the atoms inside of a universe-sized cell? Like, I'm just a ribosome, like, doing my thing on whatever it is my substrate is.
Should be on Hollywood. You could have another sci-fi movie.
I would pay money to see that one. I've seen a few hints at it, right? I mean, the fractal universe idea, I think, has been played out a few different ways, but
Yeah.
it's,
Well, that's kind of what we did in our universal cycle theory book, and essentially the same thing. And in fact, there could be, outside of what we observe, there could be another vortex that is larger than that contains the universe that we know of. And so I think Kashlinsky, I don't know if you heard about, I mentioned their work. They essentially showed that galaxies were tending to move in a certain direction that they can see. And that implies that they would use attraction, right? So these things are really being pushed to some other larger object outside of what we can see. And I think that's one of the reasons we have the multiverse, parallel verse, and so on. These theories are compromises to try to get out of the Big Bang somehow. And these are universes that have their own banging or whatever, and so on. So remember at one time the galaxies were considered island universes. I don't know if you ever heard of that thought.
Yeah, I mean, they thought the entire universe was our galaxy until about, what, 100 years ago or something?
I think until Hubble discovered the Cepheid variables, right?
Yeah, well, that is true as well. So, but anyway, Andromeda, you can see with the naked eye, almost binocs, certainly. And there it is. It's a fuzzy thing. And at one time, they didn't know it was full of stars and just like our Milky Way. And that was just one. And now we got 20 trillion of them.
Well, it's it's a resolution paradox, right? Like, I look at all this space stuff and I can't help but be convinced that we're just we're just babies in a library. And we've learned to read the alphabet book, which is B is for B.
A lot of it is popularization, though, too, because when I talk to some of the best astronomers that I know, I ask them, what do they mean by universe? And they'll say, everything we can see. And then I'm like, oh, the birth of everything we can see. Is all these things start to make a lot more sense to me. Even the Big Bang, when I'm like, oh, you mean the provenance of what you can see? Where is all this light originating from? I can almost start to make sense of what they're talking about at that point.
Well, okay, so example, for dark matter. So if there is a collection of things that you can see, but also a collection of things that you can't see, but other things can see, then they would interact without you being able to see them. Right? So if you assume that if you assume that light is a direct interconnect, so if you assume that the universe had a moment of emergence where there was, again, biological metaphors, there's a seed that sprouts, and there's a process of change. And I'm not saying that, like, I inherently have a preference for, like, big bounce or cyclic universes where there's this birth and arc of progression and then shift and change, and so it's eternal, but it's not.
Those ideas I call reformist. And see what you're trying to do. And reformists, we have 10,000 people, like I said, that are opposed to the Big Bang and relativity. Most of them, there's 3,500. Hamon says there's 3,500 theories, different theories held by these folks, and no two of them ever agree, and they're mostly reformists. What a lot of them have done is they're engineers and they're physicists too, where they have done the math and they have found some errors, like we did with Einstein's. He automatically assumed that T equals L. What that means is that time equals length. That's how he got his 4 dimensions. He has that in special relativity. We have a paper on that. So these kind of things that they're talking about are just like totally impossible. That's the thing. And the reform stuff is a problem because you'll have somebody will pick a little part of it and say this is really important and stuff. It's very hard to get the broad picture. This is what I've been trying to do, is with starting out with the assumptions, working on what does that lead us to if we use the correct assumptions. And I'm only assuming infinity. Nobody else can do anything different. But they have assumed infinity, and and they're talking about the universe being uncaused, like we were saying. Sometimes it has a cyclic universe. It comes into being, out of being, and so on. Some people like Krauss talk about, sort of.
He talks about a universe from nothing.
Yeah, and universe from nothing. Particles coming in and out of existence. So that's there. People have thought of that, and there are plenty of cycles. And one of our books, one of our main books, is about cycles, and not that, just plain cycles. And there are so many cycles that we see. That's what we're seeing with the rotations and revolutions of planets and so on. So, and a lot of times, like we have a climatic cycle. We're in a warm period now. Eventually, there'll be another cold period, and so on. So that these cycles occur, and we don't always know why. And I think why I like unienvironmental determinism is because it begs that the universe must be essentially has to be infinite. So because you always have an inside and an outside. One of my blogs, for example, had a picture of a log cabin and the trees around it. And the gist of that blog was that everything must consist of something. In order for the universe, in order for things to exist, the universe has to be infinite. Everything that you see is made of ingredients from elsewhere. And that's why you need to have an infinite universe. You can't just have an empty, nothing, dark energy and make stuff out of it. It's not going to happen.
Well, I guess the way that I imagine it is like we've I think come down on the side of light being the result of an interconnection between objects.
I mean, that makes most sense to me.
Do you know Carver Mead's work?
I think so.
He's a Caltech electrical engineer who worked for a long time in the semiconductor industry, and at some point got really, really fed up with quantum.
Well, he studied under Feynman too. He was
colleagues with Feynman.
Yeah, but he went to all the lectures and stuff.
Yeah, so he was basically deeply, and I mean, I think that you have to understand physics very, very well in order to be able to make innovations in something like the semiconductor. And at some point, he was like, "Look, The mathematical equations work really, really well, but I don't think that the story that we've built on top of them makes a lick of sense. And so he dug back into the 1920s, and what was the chemist's name?
G.N. Lewis.
And he cites G.N. Lewis, who is a chemist who basically was an early 20th century advocate of a much older idea, which is that light is the product of interconnection between atoms. If you have a one-atom universe, you can't have light because they're not particles that are just shooting off of an atom. It's the disequilibrium between two atoms that allows for a disturbance in the connection, which is what the light is. Okay, so if light is the product of connection between atoms, then there must be some kind of physical limit on either the number of connections that you can maintain or the distance across which you can maintain those connections. And so it's entirely conceivable for me that the universe is the extent of what we can see, but if you were to go to a different place in the universe, you would see different stuff. And so there's an infinity, but there's not an infinity of what you can see.
Locally.
You're limited by
Sure.
what is around you. And so that's the easiest way for me to think about infinity, which is that there are inherent limits to your own perception based off of your locality, and that shifts as you go to different places.
And that's probably why they'll have to build several more generations of these telescopes, right? And keep pushing back the date of these objects, right? And find higher and higher redshifts. And then it's just going to have to become so absurd and disgusting to look at some point that people are just like, well, that doesn't work. Like, we just can't. It's too gross at some point.
Or like, what if we get beyond the heliosphere and all of a sudden, like, imagine that we could get a telescope out beyond the heliosphere. Would we see different stuff? Like, is there something about the light passing through that is occluding a significant amount of things that we can see?
You'd always see something different. That's what infinity gives you.
Yeah.
Yeah, right. That's why it's so fascinating. You know, like all the stuff they're coming up with now with the James Webb telescope and so on. Just imagine what they're going to be seeing. Actual planets going around other stars, and maybe they'll see some blue and green. Who knows? You know, I'm not sure it's that good, but we can always get better instruments, and that opens up our view, and we get out of our little myopic box here that we're in, and we get out of it, and that's the exciting thing about it, what's going on right now.
Hey, why vortexes?
Because
That's interesting.
I guess the transfers.
I don't know if you'll have to read in this book. I a little bit on where does matter come from. And if you want to, you can take a look at that. What I get is sort of like based on relativism, which is remember the no two particles being alike. If we do have indeed ether, which I'm pretty sure we do, then the individual ether particles will have varying shapes and masses and so on. Okay, some will be bigger and some will be smaller. Remember that they'll be banging around. They're moving on at the speed of light to interpartically. I think one interesting thing is that in the atmosphere, remember sound travels at 343 meters per second. And the interparticle motion is about 50% greater, 515 meters per second. So I think with light, the same thing. The particles of light, that is not really particles of light, but the ether particles themselves, the interparticle motion is something on the order of 1.5 c. And when these things are crashing around at those kind of velocities, if you have a bigger one and a smaller one, guess what's going to happen? What happens? You have the sun and you have the earth, and it goes around, right? So why is that? Because it's being protected by the mass of the large body. So this little guy is going to hang around, just like I used to hang around my bigger friend in high school who was twice my size. he was a good friend to be around because I had some protection from him. See? So anyway, these little particles then are going to rotate around, and that's where essentially I think that ether is a precursor to all matter. And so what you're seeing is ether complexes, and it's essentially a slowing down of these ether particles. That's what's happening. One example I give sometimes is, you know what a roundup is in Western movies? The cattle have to be settled down for the night, and so what they do is they get them going around in a circle. They're still going 3-4 miles an hour, but they're going around a circle. Eventually, they slow down, and that's what we're seeing here. Is that it's kind of a roundup. That's what you're seeing for these. That's just speculation that I have about where does matter come from. It has to come from somewhere else in the infinite universe. There's no question about that. And so you have all these different forms of matter, and they're all slowing down to some degree. And they're not traveling at 1.5 anymore. They may be going around at 1.5, like an atom. Electrons, I think of them as going around the nucleus at something like C. But again, I don't know how the heck you measure that, but that's the kind of thing. So anyway, it's a slowing down. So here you are. You're a bunch of slowed down ether. How does that knock you out?
I do think it really starts to change your perspective on things, and a lot of these old experiments start to make sense when you realize that whatever this fundamental medium is, it's not separate from the things of ordinary life, right?
Exactly.
And that's something that bizarrely seems to have eluded the early, like the venerable forefathers of all of the thought that we had at the end of the 19th century. It's very strange how they treated it as a separate substance, and maybe Michelson-Morley disproved that it was a separate substance, but that wasn't the conclusion. It
had to be entrained, and that's why it got no result. It's like measuring the jet stream in your basement or in your backyard. You're not going to get very much of they actually got a small measurement about they're looking like 30 kilometers per second, and they got maybe 5, and they called it, well, plus or minus, and that's a null experiment, right? So that's what you would get if you were measuring stuff in your basement or in your backyard. Your measurement of the jet stream would be pretty low. You might be some effect because there's westerly winds, but nevertheless, that's what they found. And people that want to believe that there's no ether would just eat that up. And of course, Einstein, he claims he never even read Michelson-Morley. I kind of doubt that. I think he probably knew that this was his in for that. And
it's really interesting that Lorentz developed a similar relativity model that did involve an ether, and it was equally predictive as general relativity.
And Maxwell as well had ether, and Descartes. Interesting thing. I respect Descartes. Normally, I think of him as a dualist, but in his time, that's to be forgiven. But he did use ether. He gave the name ether with an A-E. I used to use E, and that screwed up things because it got confused with the ether in the lab. So using the letters that Descartes used, and he said that ether was the medium for light and also caused gravitation. And so I haven't changed a whole bunch from Descartes, really, because I'm just saying the same thing.
Yeah, I always use the Descartesian AE too. I just feel like it looks more cosmic and awesome.
I guess my last question is about your background in geology and soil sciences. Are you still focused on that work, or are you mostly focused on physics?
Still consulting, yeah. Currently, I do pedochronal paleoseismology, which is a facetious term for pedology is a study of soils, okay? And pedochrono, you know what that is, time. Pedochronal paleoseismology. So it's using soils dating for determining prehistoric earthquakes.
Wow.
So that's
Whoa.
what I still do. And in California, we have to have building setback from faults that are active, like the San Andreas, the Hayward Fault, and so on. And one of the things that I do, I help the geologists determine whether a fault's active or not. So right now I'm going to be working on one in San Bruno, right next to the San Andreas. This would be a secondary fault. So a lot of times you get smaller ones off to the side. And what they'll do is they'll put a trench about 10 or 15 feet deep, perpendicular to the trend of the fault. And then they'll see the soil. So what I look for is unbroken soil over the whole trench. And then this soil has to be at least 11,700 years old for it to meet the law's requirements. That's the Holocene, time since glaciations. And so I will look at the characteristics of the soils. For example, if you have a reddish soil, quite often it's older. If you have a soil that has a lot of clay deposited in the B horizon, remember when you garden, the upper soil, the black soil, is what you really like for gardening. Below that is some hard stuff, especially in the summertime, you can't get through it. And then below that is the C horizon, which is lighter colored. So that's the kind of thing that I do. And I've done other work like landslides and so on. We did earthquake planning scenarios. We would hypothesize an earthquake and then what would happen to the infrastructure as a result. And so that's the kind of stuff that I got involved. I was working with the California Geological Survey to do that stuff for about 30 years. And
Can you
yes.
Oh, can you tell me when the next California earthquake's going to be so I can avoid it because I go down there way too much?
Any day now.
That's what I was thinking. Yeah, I'm so scared. I couldn't stop thinking about it. We just spent like about a month down there in the Bay Area. And
So we're really bad about predicting these things. Actually, what we have done, we can measure the what we call the geologic slip. So when a fault moves, especially the ones around here that move sideways, horizontally, we can measure how fast they move. So we did some of the first work on the Hayward Fault and measured 9 millimeters per year. And that also moves about a quarter of an inch a year, about, maybe 5 millimeters a year, just in creep. We call it's aseismic. There's no real earthquake associated. Anyway, we use that. And then one example I like to give is the San Andreas in 06 had 20 feet of movement. That's 240 inches. Turns out that it's slipping now at about 1 inch per year. So you can do the math, figure out when's the next earthquake. So it's 1906 plus 240 years, plus or minus 60 years, of course. And then you get some idea when the next one's going to be there.
Does the slipping dissipate some of that energy though? So it doesn't have to have such a big consequence?
Well, not this creep doesn't, the small amounts don't make any difference. So.
Hold on, I'm trying to wrap my head around how you came to that calculation.
Oh, okay. What you do, say a stream crosses your fault. What happens is that it would move sideways, right? So this stream would be on this, and then further away it would be this way. So we measure this distance, and we can do this through buried streams and stuff like that. And so then we get a measurement that way. And in the case of the measurement I mentioned for the 06 earthquake, this is north of San Francisco. There was a fence that was offset 20 feet. So that's what happened in 06. So we figure if it repeats, then that's what we would get. And right now we can measure by GPS and so on, we can measure how fast the plates are moving some distance away. So we get an idea of this is all kind of stuck north of the Bay Area. But so that's what you do. And
so there's like a traffic jam where you expect the earthquake to occur at, something like that, and everything else is moving, and then all of a sudden it has to pop at some point.
Yeah, right. So it has to do a lot with generally speaking, the plates are about 10 kilometers thick. And some, in the case of the Hayward Fault, we think there's a stuck patch in the middle of that 10 kilometers down. And that's what gives us earthquakes, because the Hayward Fault has, just like the one in Turkey that just popped off, it has creep. That's an aseismic stuff. Every year it moves gradually, and then it has earthquakes too. And at first we were puzzled about that, because on the Hayward Fault there was an earthquake in 1868, and then there supposedly was another one like 32 years later, and say, what? Actually it was 1830. They said 1836 to 1868, and that's 32 years. And I was always puzzled about that. I ended up changing the location of that 1836 earthquake over to San Juan Bautista. So it doesn't affect Berkeley anymore. So Berkeley is going to get a really big earthquake right through it.
Oh boy.
So the last one was like 30 years ago, right? The Loma Prieta?
Yeah, Loma Prieta in 89, yeah. Right.
About like Bay Area geology, do you have any sense of when San Jose was last underwater? Because it has to have been underwater at some point, because you look at a relief map.
Pretty flat, yeah.
It's pretty, and it looks like a floodplain. I see prehistoric lakes everywhere, and Shilo's always laughing at me, but I'm pretty...
Every time we go out in the woods, Nasia's like, there used to be a lake here. There used to be a lake here, everywhere. Like, probably, yeah.
Well, you have two things happening. One is alluvial fans. So you get erosion from the hills, and these fans spread out and cover the ground, and then they'll move around, and so you'll get what we call, alluvial cone or fan or whatever. And so a lot of that is because of that. As far as the lake thing, that the Great Valley was a lake and drained through the area of the Carquinez Straits. Mm-hmm. One reason it drained through there is that's the lowest spot in the East Bay Hills. Mm-hmm. So what better place for it to go through? And it's gone through that place for about 1 million years, whereas previously it went through Monterey area. Mm-hmm. So but anyway, a lot of the Great Valley is like 20-foot elevation, and at about 122,000 years ago, sea level was 20 feet higher. So that was one reason that was probably filled up at that elevation.
There's something weird about growing up in California, because when we moved to Portland, the geology of the place was really central. Everybody knew the story of the Columbia Gorge. Everybody kind of knew the story of the Missoula floods. But I lived in California for 20 odd years, and the geology of the place was, earthquakes, but there's not a cohesive story of how the landscape was formed, and I was always really surprised by that.
It's a complicated area, that's for sure, because at one time it was like, by Eureka, there's plates are subducting, one is going under the other, and that happened also in the East Bay area. You remember going through the Collicott Tunnel, Highway 24, and you have these rocks that are almost vertically, and some, in fact, the units are overturned. They were deposited like this, now they're flipping over. And so that was from the fact that these plates were one time crashing together at that point. Mm-hmm. And they're not doing that anymore, but now it's horizontal and strictly horizontal, pretty much. And so it's very complicated to be able to get, to tell someone, this is exactly how this works. And you could never do it without talking about the seismology, because of all the faults being so important there.
Yeah, definitely.
And I think in that regard, I think maybe it's just easier to do Oregon. I used to live in Oregon too. So, I got my degree at Oregon State. And so, it's... And
the basalts simplify things, I feel. Well, like the basalt rocks, because they're like this lid on the landscape. It's easier to tell the story of what happened to the basalts than it is to tell the story of what happened to this.
Yeah, the Columbia is like that, so you can that's pretty easy. But the Cascades are complicated too. And I did my thesis on Crater Lake, so I did neutron activation analysis for that, and That was always kind of interesting because we had soils all the way out to the northeast corner of the state, and we wanted to show what the soil formation was like as a result of these ash deposits that came from Crater Lake. So, and we would fingerprint them. I put them in the reactor, and we would hit them with neutrons and then get about 25 elements that were radioactive, and we could measure the amount of the various trace elements, and we could compare one sample with the other, and then we would be able to tell whether or not we had only Mazama ash, because there were a lot of other ashes around. In fact, one of them was from St. Helens, and it had come on top of our Mazama sample in the far northeast corner of Oregon. And we traced this in peat bogs. You could put a drill core down, come up with a couple things: carbon below, carbon above, and the ash in between. And we got beautiful dates because Mazama erupted 7,000 years ago, and this St. Helens unit was about 3,000 years ago. And it got thicker as it went towards Mount St. Helens. We did this work before the big eruption in 1980, which we kind of predicted because we saw ever more ash deposits as we went towards Mount St. Helens.
Very cool. Yeah, I love I mean, we live on the surface, and so we have a tendency of looking at the surface and being like, this is the full story. But geology is really the opening the doors of history in a way that few other sciences are. Very direct.
Yep.
Very cool.
Exactly. Yeah.
Yeah, well, I just hope that y'all get it over with and get that earthquake out of the way so I can come back to the Bay Area without worrying about it.
Oh, I don't know. It could be. We did a scenario for the Humboldt area, and it was kind of interesting because we had hypothesized an earthquake. We had to say, well, how big should this be? Because it's a subduction earthquake. And we figured, well, it could be about a 9.2 or something like that, pretty big. And I argued for extending it past Oregon into Canada.
Oh, no.
Yeah. And guys said, no, let's just keep it in California. But the reason, I knew there were carbon dates that there had been an earthquake 300 years ago up along the coast, a subduction earthquake. And they didn't want to put that in there. But I said, look at this. You got samples all along here 300 years ago. And why do you figure it's not going to extend up there? Well, then eventually some guy from Japan found that they had a tsunami on, I think, what was it, January 26th or something in the year 1700 or whatever.
That's right.
And so, 300 years. And so that was kind of like, okay, should have done it. But
it's creepy if you go out there to the Oregon coast. It's very young feeling. I mean, like 300 years young, but it doesn't have that old feeling of a forest deep inland. And it's kind of eerie. You can actually see some of these, I think they call them ghost forests. Yeah. So like, half, these trees that have had their limbs ripped off a long, long time ago. And
you're talking about the pygmy forest and stuff?
No, I think that it's down in, I don't know exactly where it is, but there's places where the land subsided sufficiently that
and you had dead trees, Yeah,
and so they're all just stumps, but they're still in the surf.
Yep. Yeah, that's what happens, and it's kind of interesting. It goes down and also goes up. In one place it'll go up, and the other place will go down.
Yeah, so hopefully you'll be on the place that goes up when it happens.
I just want to get it over with personally. I just want it to happen.
Well, we figured that one is still 300 years to go, so maybe we'll be okay.
Oh, cool. I'll stop worrying when I go to the coast.
Yeah. Well, you don't worry. I never worry about it. I was living next to the Hayward Fault, about a kilometer away, for 48 years. And I always was asked, when's the next one? And I'd keep saying, any day now. And I never got to experience it. So,
I hope you don't.
Well, I don't know. What I had done there is what you do is a seismic upgrade. Make sure you bolt the foundation and everything. And
that's what I was going to say. It seems like people in these earthquake states have gotten pretty good. Like the huge, what was it, the Fukushima earthquake? in Japan, the earthquake itself didn't kill anybody. I mean, there was some
yeah.
deaths from the tsunami, right?
I mean, a
But
lot of deaths, 200,000.
yeah, I think it's 20,000. It doesn't matter. A lot of people died from the tsunami, but nobody died from buildings collapsing on them, which is pretty awesome. And I wonder if the Bay Area hasn't figured that out by now.
You know what hasn't figured it out is Portland. Have you seen the
Yeah.
freeways in Portland?
Brick buildings are the baddies, right? So you
The
got a bunch of
bridges
those.
too, yeah. It's just like
bridges and
all
so
these
on.
bridges that look like they're gonna fall down without an earthquake almost.
Absolutely.
Yeah, if you go to Seattle, there's a you remember the what is it, Cypress overpass that fell down in the '89 earthquake in Oakland. They've got one like that same genre, you know, and so about 1937 or something. And I think they should have a sign. I think they do have a sign. Driving on this, you know, is risky, and that
Hurry!
kind of thing.
Yeah.
Beware. It's your fault, and all that. So the Japanese have done really well, and we've had cooperative agreements with them and worked on earthquakes a lot, and they have done a lot. And of course, they're living right on the big one there. So they've learned how to build. One of the big problems had been I gave some talks for the UN in the Soviet Union and in Russia to 90 and 91, and we actually had an engineer with us when they were building some of their construction. What they do there is they build tilt-up high-rises. You know what a tilt-up is? You make a wall flat like this, and you tilt it up. And in California, we just have one story. We hooked the corners together with rebar or whatever. And the problem, though, in Moscow is that they were building these 10 stories high. And in Armenia, earthquake of 75, 25,000 people died. And one of the things that the Russians or the Soviets didn't do is they were not allowed to travel and talk to the Japanese and people elsewhere in the world about how to build these things. And all the designs were given out of Moscow. So you're in Kazakhstan, Armenia, so you build it our way. And tilt-ups were the way. So there's a lot of those buildings still around. And when we stayed in, I think it was Frunze, we ended up taking a lot of before pictures. Because one of the things they had there was beautiful buildings, you know, like a lot of glass and buildings on stilts with no horizontal bracing. So these things were death traps for sure.
Yeah.
Just another reason why I won't be going to Russia anytime soon.
There you go.
Very rational fears.
I am trying to learn the language though, just in case.
I mean, I think that this kind of ties back into to put a bow on the conversation. The ability to talk to people from different backgrounds, from different philosophies, from different ways of looking at the world is the path to actually creating a functional one. And I think that we have a lot of intellectual barriers that are in place right now that prevent people who have ideas from being able to enter into deep conversation with those that seem to have their hands on the wheel of consensus, so to speak. And that's kind of what we're trying to do here. Is we're trying to open up the space.
I think you're doing a great job. You've got some details I was impressed with too, I must say. You got the Sagnac experiment down.
Well, that was Wikipedia.
Smart and pretty. It's just
that makes everybody smart, right? You know.
Certainly
Be careful of AI though, because I did an AI and I died back in 2019. It turns out.
Oh no!
Yeah.
Well, I'm glad that you came back from the the river Styx to see us today.
Yeah. So don't believe that AI stuff too much.
That's incredible.
But you can do.
Yeah. Okay. Well, do you have any closing thoughts?
Oh, well, I think that's what you're doing is really great. I think that keep it up, and you should have some more folks on that don't necessarily believe in the Big Bang Theory. And believe is the word, right? Because, remember, we're using assumptions here, and they're believing infinity, and we just switch that on its head. And I think if you use that and read our books, that would be good. I try to write them, like you say, for ordinary people that, have had probably some college, of course, but nevertheless, don't have to have very much physics. I don't have too much math in these things. And, I use stuff like F equals MA. That's pretty simple. Newton's 3 laws, all that. And I think people should all know about that kind of stuff. But again, maybe they don't. That can be a problem because, it is, you're right. It's hard to be able to, especially with so much fantastic stuff around. And how do you convince people it's nonsense? That's the hard part.
Yeah, we'll put links to the books in the description so people can get their hands on them.
So you got but they're all on Amazon, so you can pick them up there. Yeah.
All right, yeah, folks, grab these books, check them out.
Oh.
You've got a blog also, which is pretty cool.
Yeah,
And you can get a lot of these ideas.
That's medium.com. Put my name in, and then of course I have a regular blog too. I guess did you see that one? It was scientificphilosophy.com or
Yep.
.org. Yeah, that as well. And then you can always look up glennborchardt.com, and it gives you links to everything.
Great.
Awesome. Well, thanks, Glenn. I really appreciate you giving us your time and coming by.
Yeah. Very interesting discussion.
Yeah, it was fun to meet you.
Yeah.
All right, take care.
Have a good one.
See ya.
Bye.
Yeah.